we shall begin our session. So in the session, I'm going to discuss about different kind of machine learning algorithms. How by this time we are familiar with the different kind of machine learning algorithms. The question is how can we evaluate these the machine learning models and their performance? Okay, that's what are the different kind of performance measures are there in the machine learning literature? How we can make use of. So if I'm taking machine learning models like a supervised and supervised model. In the supervised models, we will have a classification, regression, and reinforcement learning, and unsupervised, we will have a clustering techniques. So when you are proposing a new algorithm in any one of this area, or whether supervised or unsupervised, so you have to compare, right? So how do you compare it, and how do you claim that yours is performing better? The topics which I'm going to cover in this session is the introduction, then what are the different kind of estimation strategies, how we can estimate different kind of accuracies, true accuracy, predictive accuracy, and all, and coming to the error estimation by using loss functions, and especially it is useful in the regression analysis and some statistical analysis for the like chi-square test or t-test and p-test, and similarly, if the accuracy fails, what are the other performance measures are there in the literature, and lastly we will cover the RLC. So this is as far as the supervised learning is concerned. When unsupervised learning is concerned, so what are different kind of performance measures are there to deal with these unsupervised learning algorithms? We will see soon. Now, so what is this measures and sensitive analysis all about is a classifier. I think you know what is the purpose of the classifier. A classifier is used to predict an outcome of the test data. So you will divide the data to training and testing. So once you divide it, then what you are going to do? So once you have divided the data set into training and testing, and you are first with the help of training, you are trying to build the model. And its capability, the learning capability is tested again as the test data. So a classifier means the trained classifier is used to predict an outcome of the test data. Such a prediction is useful in many applications. Of course, we have seen different kind of applications starting from the stock market prediction to the what is called decision making process and weather forecasting and all this stuff we have seen. And even image classification also we have seen. A number of classifiers. 1 second. Okay. And so we have seen different kind of applications of this classification algorithms in the literature. So there is a need to estimate the accuracy and performance of the classifier with respect to the few controlling parameters in the data sensitivity. So there are some hyperparameters. For with respect to the hyperparameters, so we have to estimate the performance of your classification algorithm. So that in terms of accuracy or sometimes the behind the accuracy also you have to look for other alternative performance measures. So if you want to assess the performance of any classifier, any supervised model, so what you have to do, you have to split the data set into training and testing. Yes, this is obvious. The training is for building the model and the testing is for the what is called observing evaluating the performance of your learned model. So there are different strategies we will follow in research to build these partitioning of training and testing data sets. So there are different strategies are like if you see these strategies will be discussed in the estimation strategy. The estimation strategy will talk about what are the different kind of ways we can partition these data sets, the training and testing. And after that we will discuss about the metrics for the measuring accuracy, metrics for the measuring performance. So what are the different metrics are available to estimate the accuracy, means how accurate your model is predicting the unseen data or classifying unseen data. And if there is in presence of in the absence of accuracy, what are the other performance measures we have to take into the consideration to evaluate the model. The first is estimation strategy. So the estimation strategy, how we are splitting the data sets. So using some training data, building a classifier based on the certain principle is called a learning a classifier. So using a training data, we will build the classifier. So after building a classifier and before using it for the classification of unseen instance, we have to validate it using some test data. So the goal of the test data is to validate the build model on the trained data. So usually training data and test data are outsourced from the large pool of data already available. So whatever the data is there, so we will build what is called training and test data sets, and training is for training for the building and test is for the validation of your model. So what are different strategies we will follow for creating of this training and testing? So one is the holdout method, and other is random subsampling. The third one is cross validation. The last one is bootstrap approach. Among all, the cross validation is very famous one. So what is a holdout method? This is the basic concept of estimating a prediction. The given data set, it is a partition into two disjoint sets of called training and test data sets. So the classifier is learned based on the training and get be evaluated by the help of test data. This everybody knows. So the question is in what ratio we have to divide the data set. So and we can consider which data set is a training and which part is a testing. For that, some people will give a 50-50 ratio with a 1:1 ratio. Some people will follow 2:1, like 70-30 ratio, so that they can partition the data set in that ratio. But there is always a trade-off between the training and testing data set sizes, because if there is a training data set is used, we can train the model very well. But the question is, can we validate such a small test data? And there is a question of the reliability of what is called test data, I mean that outcome. So that's why we should have always, if the training data is very less and test data is more, the same thing is that we cannot build the model properly. So there is always a trade-off between these sizes. If the training set is too large, then the model may be good enough, but estimation may be less reliable. That's what I said. Now next is, this is a holdout method. Next is the holdout method, we will divide into some ratio, the joint sets. So in the random subsampling, what is meant by random subsampling? It is a variation of the holdout method to overcome the drawback of over-presenting a class in one set, thus under-presenting it in the other set, and vice versa. So what is happening in the holdout method? In one class, there is a class imbalance problem. Suppose if so in one data set, one particular class samples will be more, and the testing data set another what is called some other class samples are more. So there is an imbalance in this partitioning and all. So this is overcome by using a random subsampling method. How? So in this method, the holdout method is repeated k times, and each time two disjoint sets are chosen at random with predefined sizes. So what we are doing, we are the same process we are being repeated k number of times. Means in the random subsampling, we are k times we are performing the holdout method, and we are making the final result as the average of all these values. Now the cross validation technique. The main drawback of the random subsampling, there is no control. There is no control over the number of times each tuple is used for the training and testing. So if there is a training data, if there is a data set, there is a tuple T1, tuple T2, tuple T3, there are tuple Tn. Question is, how many times the T1 will present in k times? Because in the subsampling technique, you are repeating for the k times. So out of this k, out of this t, how many times the T1 will be present? How many times T2 is present? We don't have any control over that because we are creating them randomly. So instead we require some systematic approach. So that is called cross-validation method. In that, I can ensure that T1 will present in exactly k times and T2 will present in exactly in k times and T3 will present in the k times. Then such initiation is there, then it turns into the cross-validation method. So during the cross-validation method, what we are trying to do, so the data set is divided into, so with the k-fold cross-validation, they are divided into keep 1, 2, 3 k subsets, and the fold 1, the first subset is testing and remaining all are training. In the fold 2 and the second in the fold 2, the second subset is to test and remaining all are training. So like this process is repeated for the k times, and at the last you will take the average values, right? So this is called k-fold cross-validation, and similar in the lines of n-fold cross-validation is also there. In n-fold cross-validation, so this is divided into n folds. So what will happen? There n is the number of samples, means n folds means n subunits means in each subpart we have one unit, one tuple, right? You have one tuple. So one such tuple is very small, and the training side is because that k-fold cross-validation, k-n-fold cross. So one part is testing. So the testing consists of one single sample and remaining will have test training. So like this process is repeated means it indirectly means that we are giving chance to each and every sample exactly once. Means that you are training the model with the entire data set and you are testing the data with the data set. Okay. So that's what we are doing in n-fold cross-validation, but it is very computationally expensive, Yes, in the k-fold dataset consists of n tuples divided into equal and mutually exclusive parts are called folds d1, d2, and dk. Usually, and if n is not divisible by k, then last part will have some fewer sample than k minus. So that's obvious. A series of k runs is carried out, means this process is repeated. So one part is considered testing, another is training. So this process is repeated k times. Carried out in this a series of k runs is carried out with this decomposition, and in the 8th iteration, so DI is used for the test data, and remaining all are used for the test training data. Thus, each tuple is used same number of times for training and once for the testing. Exactly, because so if you take any tuple, so in this k tuple, so every tuple. In every fold, yes. So each tuple is used same number of times, but where in the early case we don't have control over that. But here we can ensure that if a particular sample is repeating k times, means it will repeat for k times, and every sample will repeat k times. So such kind of assurance is provided for the random subsampling. Okay, and of course it will be present only once for the testing. So because only one tested. The sample is present in only one test data, because we are using the fold 1, we are using this data. So what are all samples are present here, so they are repeated only in exactly once. Overall estimate is taken an average of, to find out the overall performance, you will make the average of all these values. Now let us talk about n-fold cross-validation. In n-fold cross-validation is an extreme case of the k-fold cross-validation, often known as a leave one out cross-validation. This is also called leave one out, means you leave one sample and consider remaining all as a training, and leave one as a test case. Here the data set is divided as many folds as there in the instances, thus almost each tuple forming a training set building n classifier. So what is happening indirectly? So almost each tuple is forming a training set and building n classifier. So gradually we are building n classifiers indirectly. So in this method, therefore, the n classifiers are built from n minus 1 instances because so we are repeating for n times. So every fold you require n minus 1 instances, one instance for testing. So it means that you are building n classifiers with n minus 1 instances, and each tuple is used to classify a single test instances. Meaningful. Test sets are mutually exclusive and effectively cover the entire set. Yes, obvious because if you are in one fold it is taking one. So after n folds, your model will cover entire training set. Entire training. This is as if trained by entire data as well as tested by entire. Because if you are it is nothing but you are training indirectly. You are training your model with the entire data and testing the data with the entire data. Overall, estimation is then averaged out of. So our final value is we can make it as average of all those values. So far, the estimation of the accuracy and performance of the classifier model is concerned, the n-fold class validation is comparable to others. So even if you are performing n-fold class validation, but it is very computational, but still it is suggestible to use when the data set is small. So the method is extremely beneficial with a very small data set, but larger data sets, k-fold class validation is better. So for the smaller data sets, n-fold, smaller data set, n-fold, for a larger data set, k-fold. Usually k is either 5 or 10, 5-fold or 10-fold classification. The last step is last one is the bootstrap method. The bootstrap method is a variation of repeated version of the random subsampling. So what if the random subsampling is there and the repeated version of the random subsampling. The method suggests the sampling of the training record with replacement means random with replacement means we are same record is being presented multiple times. That is meant by replacement. Each method the method says sampling of the training records. So what there is a data set. So you will randomly pick up one data set to create a training data set, but there is a chance that same data set is also being selected. So now what is the chance? We will see now. So each time a record is selected for training set, it puts back into the original pool of the record so that it is equally likely to be redrawn in the next iteration. Obviously, so once I select it, so then again there is a chance that the same sample can be selected for the constitution of your new training data sets. In other words, the bootstrap method, this bootstrap method is used where we can use this bootstrap mechanism. Any idea? Yesterday, I think last class we discussed. I think. Where we can use this bootstrap method. In ensemble, where we can use it. I'm giving some ensemble, at least in ensemble. Bagging. So the bagging is in the bagging, so we will use the bootstrap method to create the multiple data sets. The rationale of having this strategy is that let some records be occur more than once. That is the idea. The samples of both training as well as the testing. So this repetition will be allowed in both training and testing. So what is the probability that a record will be selected more than once? Suppose if I am interested to find what is the probability that it gets selected in one particular tuple or data sample, what is the probability that it will again select the, so it is a 60. So this is the proof for that, and the probability is nearly 0.632 value, and it's sometimes it also called 0.632 bootstrap method. So from this what we can show the top 64% more frequently occurred records are constituted as a training data set, and testing data set will be the remaining records. So now, so once we discussed about estimation strategy, so in estimation strategy, so then we will talk about splitting of data set. Data set splitting, we have seen what is called bootstrapping, hold out method, cross validation, called bootstrap method, and hold out method, validation, hold out bootstrap method, random sampling. So those two techniques we have seen. Now what are why we require accuracy? Because when I want to estimate the performance of any the classifier, you require some performance measure. One of the famous performance measure is the accuracy. The accuracy will talk about the so what portion of the records are perfectly classified, whether it is at a positive class, negative class, but overall the accuracy is the overall measure that will on a whole how it is performed. So whether you are least bothered about how it is performing independently on each class, but as a whole how it is performing is a matter sometimes. So let's see how we can estimate the accuracy. Okay. So we have learned how a classifier system can be tested. Next, we are to learn the metrics with which a classifier should be estimated. Now, we have seen how we can test the classifier by using different kind of estimation strategies. Next, we can see what are the different performing measures are required to estimate. Okay. So now, another thing is accuracy. There are main things to be measured for a given classifier is accuracy. If the accuracy is fails, we will look into other performance measures. Now let's see how the accuracy is estimated. If A is the number of instances with a class with which a classifier is tested and P is the number of correctly classified instances, the accuracy can be denoted as P by N. Where P is the number of rightly classified samples divided out of total number of samples. Okay, N sample. Also, we can say that error rate epsilon bar is 1 minus epsilon. So the error is always nothing but 1 minus accuracy. Now, if I'm talking about accuracy, there are two types of accuracy we can see. One is the true accuracy, others one is the predictive accuracy. But if I'm talking about the true accuracy of a classifier in accuracy, when the classifier is tested with all possible cases. But practical, it is impractical, right? Because we cannot get all possible and we get all possible unseen cases in the given classification space. However, the number of possible unseen instances is potentially very large. For example, classifying handwritten character recognition, hence the measuring the true accuracy beyond the dispute is impractical. So because we have to look at all possible cases and possible cases test against all possible unseen instances. That is very difficult. The predictive accuracy is of a classifier is an accuracy estimation of for a given test data. So here you have to find the accuracy with respect to all possible cases. Here you will find the accuracy with respect to a specific data set is called test data set. So for this test data set, so this is the accuracy, right? So if the predictive accuracy for a test data set is epsilon, and if you test the classifier with a different test set, it is very likely that different accuracy would be obtained. So that's the obvious reason, because if I change the test data set, the accuracy will also be changed. So that's the reason we will, the most of the time the research paper we will explain how the partition is happened. So in what way you did your partition means you are training and testing data. So the predictive accuracy when we estimated with the given test set, it should be acceptable without any objection. So now let's see about the predictive accuracy, how we can find out the predictive accuracy. So universality of the predictive accuracy. Consider a classifier model MD developed with the training data set D using an algorithm. So we have developed developed the training data set D and using a machine learning algorithm. So there's a machine learning algorithm. So D is the what is called a data set. So on this data set, so the so and so performance is achieved. And the true predictive accuracy when M of D is estimated with the two different training sets. So there is a model with M with the data set D. If the size of this data set is T1 in one case, in that case where the performance is 95% and the size of this sample is become now T2 and now it has been shown that 70%. The true predictive accuracy with the MD is estimated with the two different training sets T1 and T2 are 95% 70%. Further, assume that the size of the T1 and T2 are 100 and 5,000 records. Based on the above mentioned estimations, neither estimation is acceptable beyond doubt because this training accuracy is no longer considered for the comparative. So predictive accuracy with the above mentioned issues in mind, researchers have proposed two heuristic measures called the loss function and confidence interval. So in the next few slides, we will discuss more about on loss function and the confidence interval. Now, error estimating using loss function. How
what are the different kind of loss functions and how we can make use of these loss function if I test okay. Let T be the matrix comprising with n test samples like x1, y1, x2, y2, xn, yn, where xi is equal to 1 to n. The number of samples is n. In n dimensional test tuples, the associated outcome yi. So it has an outcome with yi. Suppose corresponding to xi comma yi, so there is an input xi and the corresponding to label, the actual label is yi and the classifier produces yi cap, yi cap. So also consume that yi, also assume that yi minus yi cap denotes the difference between the yi and y dash following certain difference or similarity measures. Example, yi minus yi is equal to if there is a match, else otherwise it is a given. Two such loss functions are measures the accuracy or error between the yi and y hack. So those are all absolute error and squared error. So in absolute error we will update the absolute function. In the square error we will apply the Euclidean distance and we are squaring the Euclidean distance. Right.
So based on two loss functions, the test error rate also is called generalization error. So sometimes the test error is also called a generalization error. Generalization error and test error both are same. You define an average loss over the test data set T. So sometimes we have to find the average value of all the individual errors. So the following are two methods for testing this. One is MAE, mean absolute error. Another is MSE, the mean squared error. So where this is the absolute value of each and every tuple, and this is the squared error of each and every, and finding over all the training sample will give the average value. Note that MSE aggregates the presence of outlier. So even if in the mean square error drawback is if there is an outlier present, and this error term will be exaggerated, okay, and it will impact this entire term. In addition to the above, the relative error measurement is also known. Not only absolute mean average value, we can sometimes people also use relative error. So the with relative means with respect to the central value or centroid value. So in addition to the relative error measures is also known, and in this measure the error is measured related to the mean, related to the mean value y, y bar or y tilde are calculated, right. So this is the absolute value, and this is absolute value between given prediction to the average prediction. Similarly for squared error also. Right. So now let's see some of the statistical estimation techniques using confidence interval. And so in fact we know that a value of the predictive accuracy, say epsilon, then we can guess the true accuracy with a certain range given a confidence interval. So what they are saying that if given a predictive accuracy and given a confidence interval, you can identify the true accuracy, because the true accuracy is it's supposed to be estimated against all possible cases, but it's impractical. So confidence level, the concept of the confidence level can be better understood with the following two experiments related to tossing a coin. So when a coin is tossed, there is a probability that heading will occur, and we have to experiment the value for this probability value. A simple experiment is that the coin is tossed many times and both the number of heads and tails are recorded. So when I am tossing the coin for 10 times, I got 3 heads and 7 tails. And similarly, if I toss it, so and so number, if I toss it for 100, when I toss it for 1000, the value is almost closer to 0.5. Thus, we can say that the probability value is approximately 0.5, and after a large number of trials of each experiment. A similar experiment but with a different accounting is conducted to learn the probability that a coin is flipped is 20 times out of 40. So what the probability that is when I am tossing a coin 50 times, out of the 50 times should come 20. So what is this probability? This experiment is popularly known as Bernoulli trials. Now it can be stated as follows: the P of x is equal to V, where the P of x is equal to V means what is the probability that the number of heads should be 20 out of 50. So So where NCB is nothing but out of 50 C2 20. So how many such combinations will be there? P into V means what does it mean? That the P is equal to 0.5. It is a probability of particular event, and 1 minus P is one in a particular what is the probability particular event to occur. 1 minus what is the probability that particular event should not occur. And of course, respectively, the powers will be there, V and N minus V. Where N is the number of trials, N is the number of V is the number of outcomes that an event occur, and P is the probability that event occurs. Thus, if P is equal to 0.5, because when the larger the experimentation is near to 0.5, so we can assume that P is equal to 0.5, then the same thing we can pose it as P of X is equal to 20 is equal to 50C20 into 0.5 into 20 into 0.5 into 30. So its value comes around 0.049. So with this, you can say that this is the way to have to calculate the predictive accuracy. Now, if you given a predictive accuracy and given a combination, how we will find out the true accuracy. The true accuracy you can get it easily by substituting its value in this formula. This is a true accuracy, and this is a predictive accuracy, and this you already know the performance of previous model, and T alpha will be confidence interval. Okay. So based on this, we can calculate whatever they require. We can calculate very easily. So what are the different uh, things we have to consider when we want to use statistical measures? A classifier test with a test size of 100, the classifier predicts 100 test samples correctly. We have to calculate the following. So observed accuracy, mean error rate, and standard error rate, and true accuracy with the combination level 0.95. So solution is the observed accuracy is 80 by 100 is 0.8. 0.8. So how we got 0.8? The total this is called predicted accuracy is nothing but out of 100 80 are classified properly, so it's 0.8, and obviously the error value 1 minus epsilon is equal to error rate will be 1 minus 0.2. Now how do you calculate the mean error rate? The error mean error rate will be n into p, where n is the number of sample, p is the probability, and standard error rate will be sigma, and this is called the square root of epsilon into 1 minus epsilon into n. So you already know all the epsilon value. Epsilon value is 0.8 into 1 minus 0.2 divided by n. So, and by using this, you can convert the true accuracy. Given a predictive accuracy, you can convert into true accuracy. This is also same. Now there is a case that once accuracy fails, then what we have to do? What are the different kind of performance measures we have to take into the consideration? The predictive accuracy works fine when the classes are balanced. So when there is a class balance, then suppose equal ratio of the classes are there, there is no problem with accuracy. But when there is a class imbalance, the accuracy is no longer serves to a good measure. In fact, the data sets with imbalanced class distribution are quite common in the data. So most of the time, you will have such kind of data sets. Okay, when the classifier a test data set with imbalanced class distribution, then predictive accuracy on its own is not a reliable indicator of the classifier effectiveness. So if I want to estimate the effective, find out the classifier performance, what will happen when the classifier test set with imbalanced class distributions, the predictive accuracy will no longer will be a suggestible measure, because there is a class imbalance. And let's see the following example, the impact of the class imbalance on the classifier performance. Given a data set of stock markets, we are classifying them as a good and worst. Suppose in the data set we have 100 entries, that 98 belongs to good class and 2R belongs to worst class. Now you tell me what is the accuracy? What is the accuracy now? The accuracy is 98%, but still we cannot say it is a good classifier. Why? Because it got 98% because of it might have classified all as a good. Even the worst class stocks are classified as good. In that 98 is properly classified, 2 is misclassified. That's why it is 2. Misclassified. So now even the 98% accuracy is there, when the class imbalance is there, this measure is not suitable to compare with the other models. Okay. Now, so far we have seen about the accuracy. So there are there are other measures are possible, but if you want to understand all the measures, you must know what is the confusion matrix. Once you know the confusion matrix, you can derive the remaining all formulas based on this confusion matrix. Let's say it's converted the confusion matrix. A confusion matrix is a two-class problem. It is a matrix of size 2 by 2. This is a matrix of size 2 rows and 2 columns. And if it is a matrix of m classes, if it is a problem of m classes, then it's a matrix of size m by n. Okay. So the dimension is determining the number of classes. Okay, class information. Now let's see for the two class problem. Okay. So the first row is talking about the true positive, and this is called false negative, and it is called false positive and false negative. So this is my actual value and this is my predicted value. Now, what does it mean? So the true positive is the number of positive samples are classified as a positive. So please try to understand because always it gives the confusion. So this positive means the positive samples are classified as positive. Because of this, it means it is a perfect classification. That's why it is a true classification. That's why it is true. Now, a positive class is classified as a negative class. If you look at false negative, a number of instances that were positive and incorrectly classified as a negative. They are positive only, but they are classified as a negative. That is called false negative. So that's why it is classified as negative, and that's why it is a false. It's misclassification. Similarly, false positive. The number of negative samples are classified as a positive. All the negative samples are classified as a positive. That's why it is a wrong classification. That's why it is false. The number of negative samples are classified as a negative. So it is a perfect classification. That's why it is true. It's a true negative. It's very easy. The number of instances, the true negative will talk about the number of instances that were negative, and the false positive, the number of instances that were negative and perfectly classified as the positive. So this false negative is called type 2 error, and false positive is called the positive or type 1 error. So there are two misclassifications. That's why it is called error. But one is type 1 and type 2 error, and the correct classifications are true positive and true negative. Now, what is the NP? The NP is the number of positive instances. What is the in this confusion? What is the number of instances? Total number of positive instances. How do I get number of positive instances? How do I get number of positive instances? From this, what is the total number of positive instances? How do you get it? If you sum it up these two, you will get a total number of positive. If you sum it up these two, you will get total number of negative samples. This is the total number of positive samples, this is the total number of negative samples, and this will sum it up with the total number of samples. And TP plus TN denotes the number of corrected classification. If you look at here, true positive, true negative, false negative, false positive. So this is called correct classification, and this diagram is called misclassification. For a perfect classifier, so this TP plus FN ideally should be 0 or near to the 0. Then you will have more accuracy. So TP and FN is 0 means then type 1, type 2 error is obviously 0. Now let's find out the accuracy of a given classifier with this following confusion matrix. Can we find the accuracy? What is value? 6951 plus 2588. Summing of all this to my total number of records. Total number of refund is 10,000. I think it is 9,552. So its value is 95%. The accuracy is 95%. Suppose if you are talking about, if I am generalizing for M by M classes, you are having a M class as a confusion matrix is a table of size M cross M, where the estimated element of ith row and jth column will talks about the number of instances of class I, the number of instances of class I that were classified as a class J. The second is which class it has been classified. First component means I will talks about the original class, and the second component will talks about this J is classified to which class, whether it's I to I or I to J something else. Confusion matrix may have to have a good accuracy for the classifier. Ideally, most diagonal entries should have large values and the rest of the entries being close to zero. That's what. If you want to get more accuracy, the principal diagonal element should have more values and other diagonal element should have very least value. So confusion matrix may have additional rows or columns to provide the total or recognition rates per class. So what they are saying that, so actually we are interested in this. Actually we are interested in here. Actually we are interested in only this one. But they have additional rows, this arrow, so this additional row. They will give some other information. Okay. Confusion matrix may have additional rows or columns to provide the total or recognition rates per class. Now tell me what is the accuracy of the predictive accuracy, and because it's not true accuracy, predictive accuracy. The predictive accuracy you already know it will be measured with respect to some specific test data set. The following table shows the confusion matrix of the classification problem with 6 classes. C1 to the C6. Then what is the classification accuracy? Yes, anybody? At least tell me how to calculate the classification accuracy. Given a confusion matrix, how do you find the classification accuracy? Yes. So take the principal diagonal elements and 6 and sum of all those values. Sum of all those values you will get it. Okay? Sum of the principal diagonal divided by sum of all the elements. Sum of principal sum of all, they will get the predictive accuracy. In case of multi-class classification, sometimes one class is important enough to be ignored, to be regarded as positive, and other classes combined together as a negative. So what will happen? We will reduce the number of classes to specific. So in that case, you will, that multi-class problem is called binary class, and of course you will have a 2 by 2 what is called this one, confusion matrix. Now, so what are the different kind of performance measures we can derive with the help of the what is called confusion matrix? So now define a number of metrics for the measurement of the classifier. So one is the true positive risk, TPR. It is defined as a total fraction of the, let's draw the true positive and true negative and false negative, false positive. Now what is the TPR? The TP by total number of positive sample P. This P and then TP by P. So this one divided by this one. So this is called true positive, sometimes also called specific sensitivity. It is defined as a fraction of the positive examples predicted correctly by the classifier. So what fraction of the positive samples are? So out of 100 positive samples, how many are classified perfectly? That is called true positive rate. And similarly, false positive rate is what is the false positive rate is? It is defined as a fraction of the negative samples classified as a positive, or fraction of the negative sample are misclassified. Okay, that way also you can say by classifier. So that is FP by N. So the F this is false. This is true positive rate TPR, and false positive rate is called FPR. It is divided. It is characterized FP by N total number of negative samples. So this metric also known as a false alarm rate, and most of the times we will try to minimize this false alarm FPR. Next is false negative. It is defined as a fraction of the positive examples classified as a negative class by the classifier. So how many, what fraction of the examples are classified as a negative class? Okay, what fraction of the fraction could be positive or negative. If you look at this is the positive samples which are classified as a negative class. These are the negative classes. These are the negative one which are classified as a negative. So the what fraction of total, what fraction of total, what fraction of is classified as a negative. So there is similarly true negative will talks about it is defined as a fraction of the negative example classified correctly by the classifier. So the TNR will give the TN by the total number of negative sample. Okay, this is called specificity. It is whether the FP false true TPR is sensitivity, and this one is called TNR. TNR is called the specificity. Now, on top of this, apart from this, there is another method is called false positive rate. Sorry, positive predictive value, positive predictive rate, or positive predicted value. It is defined as a fraction of the positive examples classified as a positive that are really positive. So these are really positive and that are classified as a positive. So this is called a precision. So now with the help of precision and recall, what is the recall? This is called a recall. Okay, the TPR is called recall. Now with the help of this precision recall, we can come up with a new measure which is called F1 score. This is the harmonic mean of both precision and recall. So 2 into RP by R plus P. So F1 refers the harmonic mean between the recall and precision. High value of F1 score ensures that both precision and recall are reasonably high. So this is the formula for precision. This is the formula for recall, and so this is the weight. How the weights are given to this true positive rate. How we can find out the what is called general performance accuracy. Okay, true accuracy, predictive accuracy. This is predictive accuracy. Once you have predictive accuracy, you can find out the error rate by 1 minus predictive accuracy. So now let us talk about the accuracy in terms of sensitivity and specificity. We can express accuracy in terms of sensitivity and specificity. This is accuracy. In terms of sensitivity into P by P plus and P is the total number of positive sample, N is the total number of negative samples, and similarly sensitivity is N by P plus P. And this is the epsilon, the accuracy in terms of the sensitivity and specificity. Now let us see the 4 cases, the 4 extreme cases. Suppose based on the various performance metrics, we can characterize a classifier. We do it in terms of TPR and FPR, precision and recall and accuracy. We can not only accuracy, we can use precision, recall, F1 score and all. So when every instance is correctly classified, it is called the perfect classifier. So when every instance is perfect means all the positive are corrected positive, all the negatives are classified correctly, and this diagonal is 0. This is called perfect classifier, and whatever the classifier achieved, this is called perfect classifier. Now what will happen? So when you have a perfect classifier, so what is the value? The TPR is high, the TPR is 1, the true positive rate is high, and a false positive rate, there is no scope for the negative alarm rate, so there is no negative, and the precision is the 1, precision is the 1, and F1 score is also 1, and accuracy is also definitely the 1. So here not only accuracy, we are using other models, F1 score, precision, TPR, FPR for comparing our model. Now look at the worst classifier. What is the worst classifier? If all the positives are misclassified, all the positives are misclassified, and all the negatives are misclassified. So then the total misclassification. So in this case, what will happen? TPR, true positive rate will be 0, and the false positive rate will be high, it is 1, and the precision will be 0. F1 is not applicable because the precision is 0, and accuracy is also 0. Now accuracy is also 0. Now let us talk about the ultra liberal classifier, somewhat liberal. So what will happen? All the positives are correctly classified, all negatives are misclassified. So the classifier always predicts the positive class correctly. Here the false negative rate and true negative rate are 0, and the confusion matrix look like this. And in this case, you will have a false positive rate is 1 and true positive rate is 1. The precision is 2 into precision to recall, and that is P by P plus 1, and F1 score is 2P by 2p plus 1, and accuracy will be p by p plus which reverse value is 0. There is another sort of classifier is called ultra conservative classifier. In that case, every sample is classified as misclassified. So all the positive are misclassified, all the negatives are misclassified. So this classifier always predicts the negative plus correctly. Here, negative plus is the false negative and the true negative are zero. So if you always classify negative plus correct or positive classes fails, that's again TPR is zero and FPR is zero. And even the precision is not able to calculate, and the first score is also not applicable. Not this. It's usually zero. Accuracy to take accuracy is zero. We have seen two cases: ultra conservative classifier and ultra liberal classifier, the worst classifier, and the perfect classifier. Right. So let's see the difference between predictive accuracy versus TPR and APR, TPR and APR. One strength of characterizing a classifier by its TPR and APR is that they do not depend on the relative size of the P and H, because so the TPR and APR its ratio is doesn't depending upon the size of the P and N. The same is applicable for FNR and TNR and other measures from confusion matters. In contrast, the predictive accuracy, precision, error rate, F1 score, ETC are affected by the relative size of the PNN. So those values will be changed with respect to PNN, but whereas TPR, FPR, and they are not changing. So FPR, TPR, FNR, and TNR is carrying on the different rows of this confusion matrix. On the other hand, the predictive derived from the values in both the rows. Okay, so you will find the predictive accuracy by taking the principal diagonal and dividing the total number of numbers. So this says that FPR, TPR, and FNR, TNR are more effective than predictive accuracy. Okay, so even the when you want to compare a model with these things, it is very suggestible and compared to the accuracy. Yes, let's take some 10 minutes break, then we will resume our session with the ROC curves. Let's have some 10 minutes break, we will resume our session with the ROC curves.
Okay, welcome back to the session. So let us discuss about the ROC curves. What is ROC stands for? The ROC stands for the receiver operating characteristics. Okay, the ROC is the abbreviation of the receiver operating characteristics, comes from the signal detection theory. Okay, so in the context of the classifier, ROC is a plot is useful to study the behavior of the classifier or comparing the two or more classifications. So this ROC curves will be used for the especially for comparative purpose. When you want to compare the, it's a visually we can easily by looking at this figure we can say that which is our performing classifier. A ROC plot is a two-dimensional graph where x-axis represents the FPR, false positive rate, and y-axis represents the TPR, true positive rate. So what is FPR? The false positive rate is FP by total number of false positive by total FP by N. FPR means, just now we have seen how to calculate the FPR, right? One second. Yes, in the context of the classifier, in the it is a two-dimension. It is called FPR and it is called a TPR. So what we are trying to do from 0 to so for different cutoffs and FPR, different cutoffs for different kind of thresholds. So we will so each and every point in the represent the first coordinate represents the FPR and the second coordinate will represent the TPR. So for different cutoffs, we will find what is the TPR and FPR value and we will draw the plot. Okay, we will see. Since the values of the FPR and TPR varies from the 0 to 1, so both are inclusive. So the FPR can be 0 or 1 or the similarly TPR can be, but it could be in between also. The two axes thus from 0 to 1 only. So each point x, y on the plot indicating that FPR has a value x and the TPR has a value y. So for different kind of cutoffs or different kind of thresholds, what we are trying to do, we are trying to find out the what is the TPR and FPR value and we'll put it in the plot. We'll put in the plot, something like that. So then we will draw, we will connect all these points, we will form the plot. A typical look of ROC plot with a few points, it is shown in the following figure. And note that the four corner points are the four extreme cases of the classifier. What are the four extreme cases of the classifiers? Just now we have mentioned. One is worst classifier and the perfect classifier. Another is universal liberal classifier, universal relaxable. Here mentioned universal ultra liberal classifier and ultra conservative classifier, and other one is worst perfect classifier. And those four cases will correspond to this. Okay. Now let's see about this. Now, if there are four extreme cases like this A, B, C, D. The C, if I am talking about C, both are 0. The both are 0 means the TPR is 0, FPR 0 means the model predicts every instance to be a negative class. What does it mean? It says that whatever is the it will classify them into the negative class. Because of that, if the TPR is 0 and FPR is 0 and it is an ultra conservative classifier. So now coming to the both are 1. So now coming to the both are 1. So it is the ultra liberal classifier means in this case both TPR and FPR 1, but the model predicts every sample as a positive class. So whatever is your sample is input, it is classifying as a positive class only. So that's why it is called ultra liberal classifier. So now coming back to this, the A and B is in A case the TPR is 1. The TPR is 1. The TPR is 1. The y-axis, the TPR is 1 and the FPR is 0. What does it mean? It means that it is perfectly classifying also. So all the positive class is classified to the positive class and all the negative class are classified to the positive or class to the positive or negative are classified to the negative. Hence it is the perfect classifier. But in this case,
It's reverse, okay? So the FPR is 1, and the FPR is in the x-axis y is equal to 0. So TPR is 0 and FPR is 1. The second example called B. If the worst class is not able to create a single instance properly, means the positives are classified to negative class and for negatives are classified to the positive. Here positives are classified positive, negative are classified negative. Here positives are classified negative and negatives are, there is no single instance which is perfectly classified. That's why it is a worst classifier. So this scenario is talking about the worst classifier, and this is the ultra liberal classifier, and this is called the ultra conservative classifier. This is the perfect classifier. As it is a perfect classifier, we are always prefer a Corvosi curve which is very closer to this perfect classifier. The curve which bends towards the perfect classifier is the best ROC curve. So let us interpret the different points in the ROC plot. Okay, the diagonal line joining the point 0, 0 and C and D correspond to the random guessing. Means if at all in the random case, so the by default value the TPR and the TPR value will be 0.5 and 0.5. That's why this curve is passing through like this. The random guessing means the record is classified as a positive or negative with a certain probability. Suppose a test set containing n positive and n negative instances. Suppose the classifier guesses any instances with a probability p, and the random classifier is expected is a performance respect to the random classifier. Okay, the random classifier is expected to classify the p classify n plus positive samples and n minus negative instances. Then hence the TPR and FPR will be is almost all equal to the P, and since TPR and FPR is always equal in the random classifier, and hence you will have the main diagonal like this is like it's passing through the origin. So the points in the upper diagonal region. So if you are talking about the points in the upper diagonal region, is all the points which reside in the upper diagonal region are corresponding to the classifiers which are good, as their TPR is good, is as good as FPR. That is FPR is are lower than the TPRs, because on that region what will happen, the FPR are lower than the TPRs. That's why it is a good region. This region is considered to be the good. Hence, X is better than Z, and X is higher TPR and lower FPR than Z. If you are talking about X and Z, same X and Z. Okay. If you compare X and Y, so neither classifier is superior to the other. Okay, but those are better than the random classifier. Suppose the point which are in the lower diagonal region, so this particular region, the lower diagonal triangle corresponds to the classifier that worse than the random classifier. Note that a classifier that is worse than random guessing, simply by reversing its prediction, we can get good results. Okay. So how can you fine tune the tuning a classifier to the ROC plot? So using ROC plot, we can compare two or more classifiers by their TPR and FPR values, and this plot also depicts the trade-off between the TPR and FPR of the classifiers. If you see the x-axis it will have the FPR and the y-axis it will have the TPR. Examining the ROC curves can give insights into the best way of tuning the parameters of the classifier. So by looking at this plot also we can fine tune the model so that we can improve its performance. For example, in the curve 2, in the curve C2, the result is degrade after the point P. Point P, the result is after degraded. Similarly, for the observation, the C1, the beyond Q, the values, the settings are not acceptable. So the beyond Q, the settings are not acceptable because the lower diagonal is a bad. So these settings I don't prefer. Okay, that means by that. Now this is we can use the regression. So if in the regression we are talking about errors, whether the mean error or relative error, the classification it is accuracy, sensitivity, specificity, F1 score and ROC curve standard. So what about clustering, unsupervised models? What about unsupervised models? What are the different performance measures are available for unsupervised models? What are the different classes? Now let's see that. Okay. So what are the different models are available for measuring the performance of unsupervised model? Unsupervised model means the clustering. Okay. So similar to the supervised models like classification and regression, we have some measures that will identify that we are being used for the comparing unsupervised models. These metrics are called cluster validity indices. Let's see what are they. Okay. The cluster analysis, clustering is a task of grouping a set of objects in such a way that objects in the same group are called cluster are more similar and when compared to each other than those in the other groups. Means when I'm comparing any object in a similar group, they are very close, but when I'm comparing an object in another cluster, they are very dissimilar. So usually clustering outcome is tested with a qualifying measures called a cluster validity index. So we required some kind of measures to estimate the performance of the clustering algorithm. So these are called CVIs. The cluster value index measures precisely how well the clustering splits the given data. So these indices are very essential to identify the performance of the clustering algorithms. It is a metric for evaluating the clustering algorithm. So what are the different kind of clustering algorithms are there in the literature? So I've taken few, but there can be others also. But for the today discussion, I've taken 4 performance measures, and namely ratio index, the intra-intra ratio index, which is proposed by Ray and Turi, and there is a dual index and the dynamic value index which is proposed by Jurangshan, and the Davis-Baldwin index which is proposed both sides Davis and Baldwin. So what are these 4 performance measures? What are these measures? These measures will is the idea of these measures is to create a compact clusters, intra-clusters, to compact intra-clusters and well-separated inter-clusters. So means what that means that when I'm looking at a given cluster, so all the points inside this cluster should be very tightly packed. So when I'm comparing any point, when I'm comparing the 2 clusters, there should be a clear decision boundary so that we can we can easily distinguish the clusters. So it means when I'm talking about the inter-cluster, so they should be well separated. When I'm talking about the intra-cluster, they should be very tightly packed or very compact in size so that we can easily identify the clusters. Now let's discuss the first thing is the ratio index. In the ratio index, which is proposed by Ray and Turi, it is the simplest one. And if you clearly see this, the ratio index in the numerator part, if you see it talks about the intra-class distance. Means when I'm talking about a particular cluster, and this is intra-class distance. So the intra-cluster should be how it look like. Should be very compact. It should be well separated. So compact means it should be minimized. By the well separated means the distance between the clusters should be the maximized. So overall we have to the minimize. So the ratio index uses the intra-cluster and intra-class distance in order to search for the optimal quantity of the cluster inside the data. So it is defined as follows, right? Now the question is how we are calculate the intra-cluster distance. If we, in order to find intra-cluster distance, what they are doing, if you look at, they are taking one particular centroid. If I am closely observing this particular portion, so a centroid and there is a point x and this is zi. So they are finding summation of x minus zi whole square. Means for each and every point belongs to one cluster, you are finding the distance of the centroid and you are squaring it. So like that for every point you are done, you are getting the spread of your cluster. So the spread. Similarly, we will get the spread of this. We will get the spread of this. Because the outermost summation will talks about the summation of I is equal to 1 to k, and that will cut, talking about n number of clusters. So for each and every cluster, we are finding the spread, and like that, the summing of all those spreads, you will get the spread of the compact intra clusters. Now, how we are calculating inter-cluster distance? So, means I want to find out the distance between each and every cluster. For that, I am taking two centroids, Zi and Zj, and minimum of I and j. So, means for every possibility between, so there are three clusters are there. So, total how many? So, 1, 2, 3. There are three combinations will be exist. So, there is a distance between Zi and Zj, and Zi here, and this is here and here. So, like this, there are three possibilities will be there. So, out of these, which one is the minimum? Which one is the minimum that I am taking? So, for all possible cases, we are finding the for all possible in between the cluster and all possible clusters, we are finding the distances. You know that we are picking the minimum one. So, for as I discussed, for better clusters, so this indices need to be minimized. What does it mean? So it means, suppose in X, what we are trying to do, suppose here in the x-axis, if you take, suppose x-axis k number of clusters. The y-axis is your ratio index value. Now what I am trying to do, for 2 number of clusters, this is the value. For 3 number of clusters, this is the value. 4 number of clusters, is 5 number of clusters, 6, 7. It means, so afterwards it is something like this. So if you see the least value is there at k 6 number of clusters. It means that in a given data set, for a given data set, and the number of clusters you have, the best number of clusters you can get it, the 6, because for this 6 number of clusters, you have a minimum value of this ratio index, means that is a well-defined clusters. What is a well-defined clusters? A very good cluster means they are very compact in size or well-separated cluster. When I am talking about individual cluster, it should be very compact. When I am comparing two clusters, they should be well separated. So such as clusters are well formed clusters. Such clusters can be easily figured out by using this technique. Now let's see, talk about another thing is a dual index, is slightly modified version. It is nothing but 1 by ratio index. So in the ratio index, the numerator is intra-class. The numerator in the ratio index, it is it's called talking about this is talking about intra-class, and this is talking about inter-class. So now it is reverse. If you look at dual index, so that distance, this is inter-class. This measure is related to inter-class distance, and this is related to the intra-class. Means the reverse of the ratio index. The question is how we are calculating the intra-class. So we are finding the distance between the all possible centroids, and in that you are picking up the minimum. And here the diameter, we are calculating the diameter. So in the earlier case we have found the spread, but now we are finding the diameter. How we are finding the diameter? The diameter is the maximum distance between the any 2 points, and such that the 1 point, those 2 points belongs to the same cluster. It means something like this. It is possible only when this x and y are two extremes, then only this distance is maximum. So this is considered as a diameter of the cluster. So that is nothing but spread of your directly the spread of the cluster. So now we are slightly low. So that's why if I want to minimize the ratio index, definitely I have to maximize the dual index, right? Because it's the reverse of the ratio index. It's simple as that. Yes, the dual index need to be the maximum to identify the compact and well separated clusters. In other words, highest value of the dual index indicates a good estimation of the fine-tuned clusters. Now there is a so far we have seen the ratio index and dual index. They fail to handle the noisy data. That's why there is a person called Judang Shen who has proposed this dynamic value index by incorporating a noisy feature. So in this case, he has, what is the formula of the dynamic value indices is, so the intra ratio plus the delta into inter ratio, where delta is a parameter which handles the noisy. The
let's see the intra ratio and how we will calculate the intra ratio and inter ratio, and we will see now. So the intra ratio will talks about the compactness of the cluster. How we are calculating intra ratio? The intra of the k and max intra means the intra of the k. Let's say intra of the k is nothing but the spread of all clusters. So this is a cluster, this is a cluster, this is a cluster, this is a cluster. So the each and every spread, this is the innermost, we will calculate the what is called spread, and like that for every cluster there is a spread. The intra k will talk to the spread of all the clusters. Now it is the ratio between the total spread divided by the maximum spread. Okay, what is the maximum among all? Which one is the maximum? So that spread is considered as the maximum spread, and we are finding the ratio. And similarly, this is inter ratio. In inter ratio, we also calculated the max inter k by the max inter. So what is how we are they are finding inter k? Between the two clusters they are finding, and which satisfying this particular the constraint. Now once it identifies the intra ratio and inter ratio, there is another parameter is called delta. So the delta will have a controlling parameter that handles the noisy. So delta value is set to 1 if there is no noisy. If there is it is 1, if there is a no noisy, then the formula is turns into be intra k plus inter k. Delta set to be less than 1 if there is some noisy. This value is less than 1 and there is a noisy. And the delta value is set to the greater than 1 sometimes when you want to get the more compact cluster. What will happen when you set the more? So you are paying more attention towards the compactness of the cluster. Hence, when you want to create the more compact clusters, so you have to set the delta value as 1 greater than 1. Then you are interested to create, you are more emphasized to create more compact cluster rather than the well separated cluster. So the dynamic value needs to be similar to the ratio or Dune index. Similar to the ratio index, the DVI dynamic value indices is also need to be minimized. Means the lower the value, better the number of clusters, better the cluster outcome. Then the last one is the Davis-Baldwin index, and of course this is also should be minimized. So in the Davis-Baldwin index, we are finding out the formula is its index is 1 by k into summation of I is equal to 1 to k and di, where k is the number of clusters. So how we are calculating the di? The di is the ratio of the di is the ratio of the there are two clusters I comma j, Si plus Sj by the distance Mij. What is Si? Is the measure of the scatter within the cluster, that is intra-cluster distance, and Mij is the measure of the separation between the clusters Ci and J, that is equivalent distance between two clusters. So this is the numerator is talking about the intra-class, means individual classes, individual clusters, and the Mij denominator is talking about the distance between the two clusters. Okay, this is almost similar to the ratio only, so ratio index only. So just we are finding the maximum ratio. So like this, it's somewhat similar to the ratio index only. Okay. So once we are finding out for which k value this dB is minimized, the dB is minimized, or the dB has a low value, that is the best cluster outcome we can consider. The lower the dB value, the better the separation of the clusters and the tightness inside the clusters. Okay. Now these are some of the references when we have taken this information. So the first one is our research article, which is published in some journal, and this is some Wikipedia resources. And this is proposed by Ray and Ture. This is the ratio index, and the last one is related to the dynamic validity indices. So there are some other journal papers, and you can refer for more information. And the question is, I want to give some CVI application where we can use the cluster validity indices applications. Okay, where we can use it. Okay. Now, so can we can use it the CVI for integrating. So, but you already know the k-means algorithm, right? You already know k-means. So what is the limitation of this k-means? Finding the k value, right? So the question is how we can find this k value. So for that we can use this cluster value indices. So how? So the x-axis is your k value, and y-axis is your cluster validity index. Suppose you are talking about ratio index. So for k is equal to, what is the cluster value index? K k is equal to 3, what is the cluster value? K is equal to something like this. You can draw it and suppose for which value, so k is equal to 10, the value is minimum means, so now that we can say, so for which value of the k, the CVI is minimum, if I'm talking about ratio index, this will, that is a perfect k for your algorithm. For if I'm using dual index, so this should be maximized. Okay? The same idea, you can use it for the identifying the k value in the k means algorithm. Right? You understood this? I will show one of the research article based on this, where we have used this. Okay. So it's a part of our PhD work we did here at SSC. Yeah. Yeah, if you look at here, so we have used this ratio index, dual index, and the dynamic value indices to identify the number of clusters in our diabetes data. So these are some of the plots. So depending on the indices, somewhere we have taken the minimum value, somewhere we have considered the maximum value to identify the number of clusters. So for ratio index, we found that in my data set, 48 number of clusters, good clusters are there. And the dual index, we found that 83 clusters, and dynamic value, we have found that there are only 39 clusters are there in your by using k-means. So these are, so we have integrated this cluster value indices with the k-means algorithm to get the k value automatically. Okay, this we have, so we have improved the k-means algorithm and on time and p-mine and diabetes data set. Okay. So guys, and with this I'm stopping my session. If you have any queries, please let me know regarding this performance measures and all this stuff. We have another 20 minutes are there. Yes. So this ROC curve is important and F1 score, and we should also know that when we have to use accuracy, when we should not use accuracy. Okay. So this I have clearly explained here. So this is refer this particular slide. Please refer it, and so there we explain clearly. So when we are supposed to use accuracy, when we are not supposed to use accuracy. Okay. So based on that, you have to cleverly choose suitable what is called suitable performance measure for your analysis for results, comparing with your results and yes guys, any doubts? And this is also a k-fold and k-fold cross in the validation. So k-fold validation is very rarely, very often used in the research papers. Okay, please try to emphasize on this. That's it. The important things are those things only, and remaining a lot. Yes, guys, any doubts? So if you are interested, if you want to know more about these concepts, you go through this data mining book, and which I written by Kaufman, and another book is this one, another data mining. So you can refer any of the machine learning book also. You can find these material. But this Vipin Kumar is very famous for data mining, and even not Tremblay, so Vipin Kumar and there's another data mining book I forgot. Okay, so I will. Yes, guys, and another thing is please focus on the CVIs, cluster value indices. So this, if you go to the following paper, I will share the paper. Those are interested to pursue in this direction. HSCS.
So we can access this. So this is a paper, so where we can find how we have integrated the K-means algorithm with the cluster value indices. And for optimizing the non-RBFN, okay. So in this case, yeah, you look at this plots and also there you can understand that how we have integrated the K-means algorithm with the cluster value indices and all. So here this results will speak about the number of clusters we formed and all this stuff. Yes, guys, and please, if you have any doubts, please let me know. It's an open access. It is a publicly available. You can refer this paper there. You want to study about the cluster value indices and how we have integrated CVIs with the clustering algorithms and all. If no doubts, I'm closing my session. Bye.